Here we go. Distance equals rate times time. This is not what Eddie was trying to communicate. That's what I think, right? So you go over here and you say, well, distance, if the rate is constant at 3 feet per second, then you put 3 into this calculator. This equals rate times time. And you draw a velocity graph. It would look like that. What's happening? The velocity is constant. The time is here. So after 4 seconds, this object would have gone 12 feet, which is the area under the velocity curve. And this is not a curve, well, it's a uniform distribution, which makes it just user-friendly to understand. We can generalize it. If we have any velocity graph, and we calculated the area underneath it, we can find out force of the curve. So what happened? The first half, what you've done through the 3 months, September, October, November, was take a curve and find the instantaneous change, find the slope of the curve. That's differential calculus. Now we're changing that to the area under the curve, and that's the second half of AB. And it's the second third of BC. So this is going to be more involved. Suppose we didn't have a uniform distribution, we had a curve. And what we want is the area under the curve, which is more practical. Yes, we're not going to get something traveling in a constant rate for a fixed period of time very often. So if this is the velocity graph, which is what? 1/8 t squared plus 1. Which is this quadratic which been moved up 1. And it's really v take away 1 equals 1/8 t squared. Yes? So we could do what's called LRAM. That's why we're doing the PowerPoint today, because this is very visual. You have to combine it with PDF. So one of the options is LRAM. And LRAM says use left endpoints of the curve to be the height of rectangles to approximate the area under the curve. So the leftmost endpoint in the domain is 0. If you put 0 in the function, you get a 1. So they drew this rectangle that had a height of 1. So the next thing is we go to the next point, which will be 1. So we're going from left to right, and we're putting these values into the function, the left endpoint. So the first endpoint was 0. The width of this rectangle is 1. In this case, the height is 1. We do the second one. If we put 1 in the function, you get 7/8. Why? Because the input would be 1. 1 squared is 1. 1/8 plus 1. 1/8 plus the rest of it is 9. 1/8 plus 8/8 is 9/8. So this thing here, right? Careful what this is. The width is 1. This is 9/8 refers to the height. Not the best way to put it. Okay. Make sense? We have these two rectangles. This one has a height of 1. This one has a height of 9/8. They both have a base of 1. Third one, you put 2 in there. 2 squared is 4. 4 times an 8 is 4/8. 1/2 plus 1. All right, so if this is 9/8, this is 12/8. The base is 1. Put 3 in there. What do they do? All right. The issue is you don't put 4 in there. You don't put this right endpoint into the function. Because this is LRAM. In LRAM, a rectangle is based on the left input. So these rectangles all hit the curve with the left value. This rectangle has a width of 1. The left point determines the height. The left determines the height. The left endpoint determines the height, and the left endpoint determines the height of this rectangle. What happens? We add them up, and you get this. But you can see from the picture that's an underestimate. You could use RRAM, same data set. Look what happens. If we put 1 in the function, we already did that. We got the 9/8. We already did this. We already put 2 in there. We put 3 in there. What we didn't do is we didn't put 4 in there. So if we put 4 in here, we're squared at 16. 16/8 is 2 plus 1 is 3. So it's the same rectangles. These 3 are the same. The first one where 0 was the input was particular to LRAM, and this rectangle is particular to RRAM. That make sense? So now we get a different estimate, which we can tell from the picture is an overestimate. So LRAM was too cold, and RRAM was too hot.
I like the analogy.
Thank you. We could do MRAM. You got to be careful. For MRAM, you're taking the midpoint. So the midpoint between 0 and 1 is 1/2. 1/2 becomes the input in there. So you have to square 1/2 to get 1/4. Multiply by that by 1/8, you get 1/32. So you get 33/32. Because this midpoint became the input, and that it's hitting the curve at the midpoint of the rectangle. Keep going. You get a different answer. But what did you get? You got an answer that was somewhere between LRAM and RRAM. Well, it isn't. Wait a minute. It isn't just. It isn't just right. Okay, but we have to go further into anti-differentiation to see what that's right. Actually, Evan had a good point. He had a good point. We don't know if it's too hot or too cold. Now what? Well, we could do more intervals, meaning, you understand what happened here? The width of those rectangles doesn't have to be 1. If we made the width of every rectangle 1/2. Now, what else did they do? The width's 1/2, and this is an MRAM grid. So you've got these different variables. These are called Riemann sums. You can do LRAM, you can do RRAM, you can do LRAM. you can do different widths. All we're doing is find all of these are methods of approximating the area under the curve. This is what how calculus is done for hundreds of years. So, get a different value. And now they're going to tell you they know the answer. We're not there yet. The exact answer is 6 2/3, the area of the curve. We don't know how to calculate that yet, but doing MRAM with 8 intervals is pretty close for this curve. Yeah. I'm really worried about that. So if you're sitting here going, well, just show me what to do, what buttons to push. And the issue is this. First of all, get an appreciation of the history of calculus. And secondly, there's plenty of time, but we don't have the exact function. We need to have an approximation method. Okay? That's the thing about this. We told you these PowerPoints use 89, which we're not going to deal with. And all of a sudden, we got way more learning objectives in a second. Here's the rate and sum, approximate definite, approximate definite. Interpret the meaning. Okay. So here is the problem at the end. So we're going to start there. We're going to come back to this in class. You want the area under the sine curve from 0 to pi. Okay? 4 equal subdivisions. So if we draw a picture, it looks like this. It's the sine wave. We're going to do an LRAM graph. 1, 2, 3, 4. What are the widths of the 4 rectangles? I'll tell you what this comes to. What are the widths of all the 4 rectangles? Number 4. Because the sine wave is 0 at 0 and it's 0 at pi. If you have 4 intervals, they're each 1/4 of the way to pi. Okay? So then you want to use LRAM, where the LRAM to draw a rectangle. You got a rectangle here, you got a rectangle here, you got a rectangle there. The left endpoint, the rectangle there. We'll come back to the answer if we do this. But that's, you just have to kind of visualize what's being used. So example 1, ready? I'm on page 264. And now they're going to involve particle motion in this. A particle starts at time 0, and they give you the velocity curve. Ready? We're not graphing the particle in our motion curve. We're given the velocity curve. The velocity function for the particle. So the velocity for the particle is t squared between 0 and time 3. So if you look in the book on page 264, here's the velocity curve. So where is the particle at time 3? 3, the input is squared, you'd be at position 9, correct? Not correct. That's the output for the velocity at time 3. What you're looking for is the area under the curve from 0 to 3. So, this is how we want you to do this. I built this table over here. And I said, all right, if I'm going to have, right, 4 intervals from 0 to 4. What am I getting 0 to 4? So this is problem 3. I got ahead of myself. So I'll draw it here. Move this up. I'm sending you, not yet. Problem 4. Yeah, so I got ahead of myself. I didn't want to show that. So for here, here's what we want you to do. For that problem, with a picture, we'll go to this picture. We want you to build an interval. So let's just do this and say, suppose you have an interval with 1. Makes sense? Let's start with the picture before. But if the width is with 1, you can go from 0 to 1. You would go from 1 to 2. You would go from 2 to 3. Then 1. For LRAM, the input would be 0, 1, and 2. That's the input. The output would be t squared. If it was MRAM, the input would be 0.5, 1.5, and 2.5. The height would be this square. And if it was ORAM, the input would be 1, 2, and 3, and we would still get t squared. What we try to point out to you before was, if you compare LRAM and ORAM, right, these two are common. 1 and 2 are common. So the output's going to be common. So what's different? LRAM is an input of 0, ORAM is the input of 3. So that's why we want to eventually get the calculator to you, because you want to use the technology to make calculations when the intervals get a lot of error. But you just try to conceptualize this. So this is really your model. It's down here to set our problem number 3. So if you're at home, so you can't see the board too well, then you can just scroll down on the PDF just to see how the implementation is written in order to have a plot for whether your height is going to be a left input, the mid input, or the right input. Right? So just set that up with a different function, and then we'll roll that out. You understand? You see what happens. Here's what we did. Ready? It's the same question, except what happened in problem 2, or I'm sorry, the exact exercise, example 1, you had t squared. And they just, well, your problem, they moved it up. It's t squared plus 1. And they changed the interval. Instead of going 0 to 3, going to 0 to 4. Okay, well, here's the interval. They have the same way. They're all a width of 1. You don't have to be, because how we're going to start doing this when semicolon. So for LRAM, the inputs would be 0, 1, 2, 3. For MRAM, halfway between these two. Halfway between, halfway between, halfway between. For RRAM, the right hand switch, 1, 2, 3, 4. But by building this interval to the left, I think it helps you build the input. Make sense? Because when you write the interval, you say, okay, for LRAM, I'm taking these values. For RRAM, I'm taking those values. And for MRAM, I'm taking halfway between. So I went to the calculator and said, okay, for LRAM, we put, ready? 0 through 3, I wouldn't count the 17. So for that thing, it should be 0, 1, 2, and 3. Here's the output, and you square it and add 1 to it. So the approximate area would be 18. And what? You put the MRAMs in there, you square them and add 1 to them, the approximate area is 25. For RRAM, the 0, 1 is no good. I put 1, 2, 3, and 4 in there, and at these numbers you get 34. So you got 3 different approximations. You got 18, 25, 34. Anybody notice something interesting about the MRAM? It's not dead center. It's not. How far is 25? It's 7 above 18, but it's 9 below 34. You'll see why that's true as we move forward in the chapter. So this is a little, ready? For LRAM, I'm not counting this last order pair, and for RRAM, I'm not counting the first order. Example 2. For example 2, here's the picture in the book. What have you got? X squared sine x. If I'm going from 0 to 3 intervals, then LRAM, the width would be 1. 3 intervals with 1. Right? The one I put in there. The width's 1 times the height. That's 0, 1, and 2. For RRAM, the width's still 1. But my input is 1, 2, and 3. For MRAM, the width is still 1, but the inputs are 0.5, 1.5, and 2.5. Then, suppose you double the intervals. If you double them, then the width would be 1 of 0.5. But you have twice as many rectangles. So those inputs would be 0, 0.5, 1, 1.5, 2, 2.5. So RRAM has these overlapping. It's got 3 as an input, where LRAM has 0 as an input. And then MRAM, the widths are still the same. We have different inputs. So it's not about the answer. I don't really care about that. You care about how you understand how this was set up. Right? So, we're not going to go to the problem for this. If you are at home, you are dismissed to do the exit ticket. We will see you tomorrow, 5 to Alpha. And then your test, matter your home or in the building, Monday. Right, so you're going to log on Monday, and I'm going to send you to the test.